Consider the Taylor series for e to the x. Use the series to derive Euler's formula e to the ix equals cosine of x plus I sine of x. Use Euler's formula to show that e to the I pi plus 1 equals 0. Okay. So what we're going to do for this is we're going to apply Taylor's formula right here. And it's something where it's kind of given. We're going to assume that it's true for now. And we're going to find e to x. So when we apply Taylor's series, the formula for Taylor's series, it's basically just going to be a pattern. And what we do to start with is we're going to find the derivative, multiple derivatives of the function. So I'm going to do f to the 0. By that I mean the 0th derivative of the function, which is just the function. So this is going to be e to the x. The nice thing about e to the x is no matter how many derivatives you take it, that's going to be the first derivative. Derivative meaning slope. It's going to stay the same. So we have second derivative of x, that's supposed to be a 2. E to the x. F third derivative of x equals e to the x. F fourth derivative of x equals e to the x. And so now that we have the derivatives, we want to do it about a specific point. We can choose any point we want. In this case, it's going to be easier if we choose a equals 0. And there's no real way to know which would be easier to start with. This is a Maclaurin series. You just do trial and error. You're like, oh, okay, this works better. So f 0th derivative at point A, which is going to be 0. E to the 0 is 1. And one of the nice things is since these are all the same, these are all going to be the same. And I'm going to write them up quickly just so that we kind of see that pattern about how we go through this process. So f third derivative of 0 also equal 1. F fourth derivative of e to the x is still e to the x, still have 1. Okay. So now we got this pattern down. We're going to write up what f of x equals. So f of x is going to equal, so the fn to the a, the first term right here, is going to be this term right there. So it's going to be 1 over n to the factorial. So our first term is going to be 0 because we're starting with 0. It's going to be 0 factorial x minus 0 because we chose a to also be 0 to the 0th power. All right, second term. Still going to have 1 over, now we're going to have 1 factorial, but now we're going to have x minus 0 still to the first power. And we're going to do this a couple more times just so we can see the pattern. So we're still going to have 1 because that coefficient's always going to be 1. Always going to be 1 when we're doing e to the x. 2 factorial x minus 0 squared plus 1 over 3 factorial x minus 0 cubed plus, and now I'm going to do the infamous ... implying that it continues on indefinitely at this pattern. All right, so now that we've got that, we're going to simplify this. So some things we can see is this section right here, that's just going to be x minus 0 is going to be the same as x, and we're just going to basically ignore this 1 because when you ever multiply something by 1, it stays 1. So this is going to become, this first term, x minus 0 to 0, anything to the 0 is going to be 1. So the first term is going to be 1 plus x over 1, which is going to be x, plus x squared over 2 factorial plus x cubed over 3 factorial. I'm going to continue on for a couple more just to make sure we got it. X to the 4th over 4 factorial plus x to the 5th over 5 factorial. And this is our Taylor series for e to the x. All right. So now that we've used Taylor series for e to the x, we're now going to apply that to prove Euler's formula. So what we just did right here was we converted e to the x to a summation of polynomials. And I'm going to do that real quick right now. I'm going to say summation. It's a terrible summation. Summation. Still mediocre. N equals 0 to infinity. So if we want to write this out, this is going to be x to the n over n factorial. So basically saying that, and this is going to be equal e to the x. So now we're going to look at how we use the definition of e to the ix to show that cosine of x, that equals cosine of x plus I sine of x, Euler's formula. So I'm going to write up the Taylor series for sine of x and cosine of x. Now, to actually find these, we'd follow the exact same pattern we just did to find e to the x. These are something you're kind of allowed to memorize, so I'm just going to put it up right now. So what we have is, for sine, it is the odd numbers. So we have x to the first over 1 factorial, and then it's going to alternate. So minus x cubed over 3 factorial, x to the fifth 5 factorial, and so forth. So, and then for cosine of x, we're going to have that equal to, make sure I get this correct, yep, x to the 0, and then it's going to be the even numbers. And in a deeper level, this makes sense because cosine is an even function and sine of x is an odd function. Not important for this, but just kind of a sidebar, like, oh yeah, seems reasonable. Okay. So now we have the three Taylor series we're going to use: e to the x, sine of x, cosine of x. We write out our function e to the ix. So we'll do e to the ix. I'm going to write this out in terms of our Taylor series. So what we're going to do is we're going to take the e to the x, and we're going to replace that with ix. So it's going to be 1 plus ix, because we replaced the x with ix, plus ix squared over 2 factorial, plus x cubed, nope, fail, ix cubed over 3 factorial, plus x to the fourth over 4 factorial, plus x to the fifth over 5 factorial, plus dot dot dot. Okay, so now we have that. And now what we're going to do is I'm going to do a quick sidebar here describing I. So I is going to kind of rotate in a pattern of 4. So when you have I, that's just going to equal I. When you have I squared, that's going to equal -1, because the definition of I is it's the imaginary number, which is the square root of -1. We get I cubed, that's going to be I to the fourth, that's going to be 1, because it's the same as -1 times -1, which is normal 1, because the negatives cancel. And then when you get to I to the fifth, that just gets you back to the beginning. 1, that's the same as I to the fourth times a single I, and I to the fourth is just 1, and that gives you back to I, and the pattern's just going to repeat. So when we apply that to this equation we just did, we get 1 plus ix minus, because we get an I squared, minus x squared over 2 factorial, and then I'm going to look up, see what I cubed is, -I minus ix cubed over 3 factorial plus, oh, this is supposed to be ix to the fourth, ix to the fifth. Ix to the fourth is just 1, so this becomes x to the fourth over 4 factorial. And then we get plus I to the fifth is, again, just ix to the fifth over 5 factorial. And we're going to do the dot, dot, dot. There we go. I know, a little bit messy. I apologize. So now what we're going to do is we're going to take a look at how these, we can write this in terms of sine and cosine. If we look at sine right here, we have x cubed x cubed. I'm just gonna circle this whole thing. Hoop, right here. This term right here. That term right there. That term right there. And I'll circle the positive part too, because it's, we know it's positive. There we go. Same thing with the cosine. So we have 1, negative x squared over 2 factorial, negative x squared over 2 factorial, negative x to the 6, x to the 4 factorial, and then afterwards we're going to continue on. So long story short, this is sine of x multiplied by I, because we got that little extra I we're picking up, and then cosine of x. So when we replace these, we're going to get cosine of x plus I sine of x, which is exactly what we wanted in the beginning. So if we look back, see what our goal was. Our goal was to prove that e to the ix equals cosine of x plus I sine of x, and that's what we got here. E to the ix equals cosine of x plus I sine of x, and all we did was we took the Taylor series of e to the x, plugged in ix in place of x, looked at the Taylor series for sine of x and cosine of x, did some substitutions, kind of zippered everything together, and right there we had Euler's formula. And then for the last part, it asks use Euler's formula to show that e to the I pi equals 0, and this isn't too bad. So I'm going to do this one quick just to kind of be complete. So we have e to the I pi. We replace x with pi. This gives us cosine of pi plus I sine of pi. Sine of pi is 0. Cosine of pi is -1. So we have e to the I pi equals -1. Rearranging that, we get e to the I pi plus 1. Oh, that's a terrible pi. Oh, e to the I pi plus 1 equals 0, which is what we're looking for. So that's how we would approach this. This is how we would use the Taylor series for e to the x, cosine of x, and sine of x to derive Euler's formula. So hope that helped. See you next time.